Engineering. I'm Dr. Wood, and this is CIVL203 Dynamics, Learning Objective 0.2, looking at inspectional and analytical reading. In this video, we're going to talk about your textbook and set up some of our major terms so that we can read the textbook well. One way you can think about a class is being led through reading the book well. Eventually, there'll come a day when your boss will give you a problem, or maybe you'll encounter a problem in practice, and there won't be a book, or there might be a book, there won't be a YouTube video, there won't be a class. Instead, you'll have a code, and you'll just have to solve the problem. And at that time, being able to read a book to increase your understanding will be a valuable skill. And this, in college, is an excellent time to develop and practice that skill. So my goal in this lecture is to help you think through how to read a book effectively and point you to some helpful resources. The first resource that I love, this book is awesome. It's called How to Read a Book. Obviously, you have to read it twice. You got to read it once to learn how to read a book, and then a second time to read it well. That's not really true. It's a great book. You should read it. I highly encourage it for summer reading. But he walks us through 3 different stages of reading a book. There's the inspectional reading, where you, in the course of maybe, let's say, a half hour, you figure out what a book is about, what it's out to accomplish. And then from there, you can decide whether or not it's worth an inspectional reading, or an analytical reading, where you would actually interpret the book. You'd understand the words he's using and the sentences and the logic and where it leads and where it's going. The last category would be an intellectual critique. So once you've interpreted the book and you can say, I understand what the author intended, not what the reader intended, what the author intended to communicate, then you can critique the book. And it turns out there's actually only a handful of ways that you can properly critique a book. But I don't want to give any spoilers. Go read How to Read a Book. Right now, what I want you to do is grab your textbook if you have it. Beer and Johnson Dynamics is great. Hopefully you've got a reasonably recent version. Say anything after the 10th edition should be fine for this class. It's full of great example problems. So if you need more example problems than we get through in class, there's a bunch in there. So enjoy that, as well as a pretty well written text walking you through the different concepts that we're going to engage with. So I want you to inspect that textbook right now. So I want you to take your textbook. I want you to look at the preface, the introduction, the table of contents, maybe even the first chapter, thumb through some of the other chapters, and answer a couple of questions. So the first question is, what is the book about? Classify the book. First, classify the book. So think about where you would find it in the bookstore. Is it fiction? Is it nonfiction? Is it theoretical? Is it practical? What topics does it cover? Then think about what the book is about, what it's aiming to cover. So now we're kind of drifting into more of the topical aspects. Being able to outline its major parts. Often the table of contents is the most helpful resource there. And then finally, you should be able to define the author's problem. So I'll expect each of you to provide some comments in this video as you think through these questions. So we'll want to be able to do that. Now, once we've got that under our belt, we can kind of jump into the book. So the first thing I want you to see is how I have laid out the major parts of the book that we're going to actively use in this class. So the first thing to say is that we're not going to cover every single chapter. There's a ton in this book. It's super valuable. But for a civil dynamics class, we can get everything we need out of these 3 chapters. And they're laid out in kind of a matrix. So we got kinematics and kinetics, particles, and rigid bodies. Easy peasy. Now, hopefully, you'll remember from statics the difference between particles and rigid bodies. For example, if we model something as a particle, we're worried about its mass, but we don't care about its size. Typically, this will let us use concurrent force systems, so there's no perpendicular distances, no moments. Simplifies things quite a bit. When we look at rigid bodies, we're now going to be considering their length, so we'll get some rotation and the moments to go along with that. And so we'll do that kind of the second half of the semester as we master particles first and then go into rigid bodies. Now, it's worth us understanding our terms and knowing what we mean when we say these different things. So the first term we'd want to understand is what mechanics is. And so mechanics in general, and hopefully you see this from the first part of your book. If you're not with me, you can look on page in the early 600s, depending on your edition, the first introduction to chapter 11. That is the front of the Dynamics Only book. They keep the numbering the same for the combo version. Mechanics is simply the study of forces acting on bodies. And so when we studied statics, we looked at forces that were in equilibrium. So some of the forces equal to zero, yay, nothing moved. We loved it. And it was fantastic. We loved it so much. I loved it so much. I hope you loved it so much. Because what we're going to do now is move into dynamics, which looks at rigid bodies in motion. Now, this kind of brings us to another point when we think about the study of mechanics. Mechanics is actually broken down into three major subgroups. We got rigid bodies, which is where we're living in this class and in statics. We got deformable bodies, which would be your mechanics and materials class that you're probably taking now or will take soon or just finished taking. And then finally, your fluid mechanics classes, looking at either compressible or incompressible fluids. Those are our major areas of statics. When we think about rigid bodies, we're looking at things that don't deform. We're not taking into account all the little bit of flex that everything experiences. And we can think about statics where, yay, nothing moves, and dynamics where, yay, everything moves. So it's going to be a lot of fun. I really love studying these topics and learning about them. I think it's such a great experience. And so with that in mind, in terms of what dynamics is, let's look at some of these other terms, these new terms here that we have to consider. And so I'm going to even out the screens a little bit so you can see what I'm writing on the board. Hopefully you see this term on the screen. We have kinematics. So it turns out dynamics is broken into two major subgroups, and the first one is going to be kinematics. And look, this looks solely at the geometry of motion. So the geometry of motion. So we're going to have to consider some variables. Some of our variables will be time, which I'll indicate with a lowercase t. That's how I write my lowercase t. We'll also have position, so where things are, where bodies are. And we'll use s when we're talking about the scalar position. So this would be in a rectilinear motion, length or distance away from an origin. And we'll use the symbol r with a hat when we're talking about the position vector. So both the distance and the direction, because it's a vector, right? So vector and scalar. Again, hopefully something you mastered from statics. You're going to see a reoccurring theme that statics really sets us up for dynamics. We're going to see the relationship between time and position that will also give us the relationship with velocity. Velocity, I'll indicate, so position is going to be blue, velocity is going to be green. And so I'm going to use a lowercase v to indicate velocity. This would be speed because it's not wearing a vector hat, so it's not dressed up for a party. It's just a magnitude. It's just hanging out. But if we put a little vector hat on there, dress it up for a party, now we're looking at speed, velocity, which is both speed and direction. The last term we'll spend our time on is acceleration. Acceleration. We'll use the symbol A, and I'll indicate accelerations in red. So we'll have a lowercase a for the magnitude of the acceleration, no special word for that. And a vector hat there when we're talking about the magnitude and direction of acceleration. And we'll talk about what the relationships is in our very next lecture, looking at rectilinear motion, just at a very high level, what the relationship is there. But kinematics is all about the geometry. So right now when we're studying kinematics, we don't really care what's causing the motion. What we care about is being able to describe the motion. That brings us to our second term, and kind of the second way we'll spend our semester is looking at kinetics, which is the relationship between force, so the push and pull, okay, and we'll indicate that typically in red, and we'll use it is something with magnitude, force, magnitude and direction, so it's a vector, force, mass, and that will be a lowercase m, and it's actually a scalar quantity, so it's just a thing, an amount, force, mass, and motion, meaning position, velocity, and acceleration. And so when we get to relationships here, the kinetics portion, we'll start looking at what's actually driving the motion that we've mastered describing in the kinematics section. So that's kind of how our dynamics is broken into these two groups, and this is how we'll work through the semester. So we'll start off looking at particle kinematics, and then we'll go to particle kinetics. Then we'll explore particle or rigid body kinematics, excuse me, and rigid body kinetics. And we'll move through that. Now, some of you may be looking at this. Is there a relation between force, mass, and acceleration? Yeah, that's called Newton's second law. That's what we're going to spend a lot of time talking about, F equals ma. So there's a lot of things there. You should be familiar with many of these things from physics. We're just going to expand on those topics as we go forward. And so that's what we've got going on there in terms of terms, kind of my color coding, and what we'll have going on from there. So I look forward to seeing you in class. Oh, quick note, units. We're talking about a force. It's going to have units of pounds and newtons. I will not use the unit pound mass in this class, ever. It's a mess. It creates a problem. So we're just going to talk about pound force, and we'll mean force there. And then mass would use slugs. Again, I'm not going to use slugs actually either. I'm going to tend to leave it in pounds second squared per foot, which is equal to a slug, to make our math work out well. Another comment to make about units is that if the problem gives you units in a particular system, keep it in that system of units, work in base units, don't translate between the two different base units. Switching back and forth between systems of units is a good way to make sure your rover hits Mars rather than going into orbit around Mars. So don't do it, just stay in a single unit system, typically the one given to you by the problem. All right, I think that's it for this lecture. I look forward to seeing you in our class time. Thanks, take care.